In this video, we'll talk about the derivatives of inverse functions. The basic principle is that if you can differentiate a one-to-one function, then you can also differentiate its inverse. You can think of this in terms of tangent lines. If we start with a function y equals f of x, which is differentiable, that means we can establish a tangent line at a certain point. The points on the graph of y equals f of x correspond to points on the graph of the inverse by swapping the x and y values. So if this point has coordinates x comma y, then we can reflect that point through the line y equals x, and that will give us a point with coordinates y comma x. So any point x comma y on the graph of f gets mapped to or corresponds to a point on the graph of f inverse having coordinates y comma x. And if we have a tangent line at x comma y on the graph of f, then that reflects through the line y equals x as well and becomes a tangent line on the graph of the inverse at y comma x. So if you can differentiate a function f at x, then you can also differentiate its inverse at y, where y is equal to f at x. Now there's a little caveat, which is that this doesn't quite work if the tangent line on your original function is horizontal, because if you have a horizontal tangent line on your original function, then the reflection through y equals x will be a vertical tangent line, which has, in a sense, infinite slope, and the derivative won't exist in a case like that. Let's look at some examples. The examples we're going to look at are the inverse trigonometric functions. We know how to compute the derivatives of the trigonometric functions, and so we're going to use those to compute the derivatives of their inverses. But let's just remind ourselves of what the inverses are for at least some of the trigonometric functions. Let's start with the inverse of sine. The function f of x equals sine of x is not one-to-one on its full domain. It's a periodic function. It does not pass the vertical line test. If you draw a vertical line that passes through one point, it will pass through infinitely many points because the function is periodic. So in order to have an inverse, we restrict the domain. And we restrict the domain to the interval from minus pi over 2 to positive pi over 2, which is this interval right here. Every possible output of sine of x is obtained on that interval. That is to say, we get values that are as small as -1 and as large as 1, and we get everything in between. So we get all of the values between -1 and 1. These are all of the possible output values for sine of x. So we get all of the output values once and only once. On this interval, the sine function does have an inverse, and we call it the inverse sine or the arcsine function. Here's a graph of y equals sine of x and its inverse. The inverse is in blue. We look at sine x on a restricted domain between minus pi over 2 and positive pi over 2. Now the domain of sine becomes the range of its inverse. So the range of inverse sine is all of the values between minus pi over 2 and positive pi over 2. Now the domain of the inverse is the range of the original function. So you can see that the domain of the inverse sine is all of the numbers between -1 and 1. So all of the outputs for sine of x, which are the numbers between -1 and 1, become the inputs for inverse sine. The inverse of sine has two common notations. One is sine to the -1, meaning sine inverse, but it's also called arcsine. Either one is common and accepted. We can do the same thing with cosine. Cosine is also not a one-to-one function on its full domain, so we restrict the domain to some interval. In this case, the interval that we pick is the interval from 0 to pi. On this interval, we get all of the possible outputs for cosine. That is to say, we get values as large as 1 and as small as -1. So we achieve all of the output values for cosine on this interval, and we achieve them exactly once. On this interval, the cosine function has an inverse, and we call it either the inverse cosine or the arc cosine. Let's look at the graph. So again, the graph of the inverse function is in blue. So this is the graph of the inverse. And we see that the restricted domain of cosine, which is 0 to pi, becomes the range of our inverse function. So we get all of the values between 0 and pi. The domain of cosine inverse is the range of cosine. So the domain of the inverse cosine are all of the numbers between -1 and 1. The inverse of cosine is denoted by either cosine to the -1, meaning cosine inverse, or it's also denoted arc cosine. Either one of these is acceptable. There's one more trigonometric function we're going to look at, which is the tangent. The tangent is also not one-to-one on its full domain, so we restrict it as well to a smaller domain, and we restrict it to the domain from -pi/2 to +pi/2, but there's a little mistake here. We don't include the endpoints. We don't include those endpoints. Tangent is not defined at -pi/2 or +pi/2. In fact, we have vertical asymptotes there. At -pi/2 and +pi/2, like so. So the tangent function is not defined at -pi/2 or +pi/2, so we actually have to leave out the endpoints. However, between -pi/2 and +pi/2, we do get all of the values. Now, all of the values in this case are all real numbers. So the domain is -pi/2 to +pi/2, but the range is everything. So it's all real numbers, not just the ones you see here, but it continues. This function is unbounded, going to positive infinity as you go to pi/2 from the left, and going to negative infinity as you go to -pi/2 from the right. So on this interval, we achieve all real numbers exactly once. So the function tangent is one-to-one on this restricted domain, and it has an inverse that we call inverse tangent or arctangent. The graph is, of course, the reflection through the line y = x, and we can see that in this case, our domain is the set of all real numbers, going from negative infinity to positive infinity, and the range is now all of the numbers from -pi/2 to +pi/2, but not including the endpoints. Again, we don't include the endpoints. The vertical asymptotes that we had for tangent become horizontal asymptotes for the inverse tangent. And we denote the inverse tangent as tan to the -1 for tangent inverse, or we can also call it arctangent. Both names are commonly used. Our objective now is to compute the derivative of these functions, the inverse sine, the inverse cosine, and the inverse tangent. Let's start with the derivative of the inverse sine. So the main tool that we're going to use is the chain rule, but we're going to actually start with the cancellation law. So we start with the fact that sine evaluated at the inverse sine of x is going to be equal to x. That's what we start with. This is the cancellation law. And what we're going to do is we're going to differentiate both sides. So I'm going to compute the derivative with respect to x of this side on the left, and I'm going to differentiate the function on the right. These two functions in blue are equal to each other. So if two functions are equal, then their derivatives must be equal to each other. Well, on the left here, we have the derivative of a composition. It's sine of a function. So if we differentiate sine of a function, we're going to end up with the derivative of sine, which is cosine of whatever goes inside that function. And then we're going to multiply that by the derivative with respect to x of, again, whatever's inside. Now the thing inside is sine to the negative 1, that is sine inverse. So that's our inside function. So let's just put sine inverse inside here. Sine inverse of x. So that's our inside function. We have the derivative of sine of a thing. The derivative of sine is cosine of that same thing times, and then we have to multiply by the derivative of whatever's inside, which is the inverse sine. Now, we don't know what that quantity is. In fact, our goal is to figure that out. But that's the left-hand side of this equation. Notice that the right-hand side is something that we can compute. The derivative with respect to x of x, that's just 1. So what does that tell us? Well, that tells us exactly what we want to know, because we can now solve for the unknown quantity. So we'll solve for this. And what does that mean? That just means we're going to divide by cosine of sine inverse. And what are we going to end up with? We're going to end up with the derivative with respect to x of sine inverse of x is equal to 1 over cosine of sine inverse of x. Now this is the derivative of the inverse sine. Unfortunately, it's not exactly in a useful form. 1 over cosine of sine inverse of x. It turns out that this expression actually has a much nicer form. And the way we're going to show that is we're going to invoke a little bit of geometry. Let's just remind ourselves that sine and cosine have something to do with right triangles. So what we're going to do is we're going to just divide this slide in half, and on the right side we're going to draw a triangle. And what kind of triangle are we going to draw? Well, it has something to do with this cosine. It's cosine of something. We want to figure out what cosine of sine inverse of x is actually equal to. That's what we're interested in. Sine inverse gives you an angle. Remember that the inverse sine has as outputs the domain of sine. The things that go into sine, and indeed the things that go into cosine, are angles. So that means that this is going to be some angle, let's call it theta. So sine inverse of x is equal to theta. Okay, well what does that mean? If sine inverse of x is theta, that means that x is equal to sine of theta. But sine also gives you something related to a right triangle. If we draw a triangle like so, we want it to be a right triangle. And if we make this angle theta, then sine of theta is equal to the opposite over the hypotenuse. Well, we know that sine of theta is x. So if we construct a triangle that has angle theta and make the opposite side equal to x, like so, then we'll have x over 1. So this has to be equal to a 1. Sine of theta is opposite over hypotenuse, but we know that sine of theta is x, so if we make sure that this length is x, that means the hypotenuse has to be equal to 1. Okay, well, how does that help us at all? Well, we're trying to figure out what cosine of sine inverse of x is, but notice sine inverse of x is theta. So really, our goal here is to figure out what is cosine of theta. What is that quantity? What is that? Well, we know how to find cosine. Cosine of theta is adjacent over hypotenuse. We know what the opposite side is in the hypotenuse. Well, we need to figure out what the adjacent side is. We need to complete the triangle. And we can do that by using the Pythagorean theorem. So if we call this length a, then we know that a squared plus x squared is equal to 1 squared. Or in other words, a squared is equal to 1 minus x squared. So a is equal to the square root of that, 1 minus x squared. So cosine of theta is equal to the adjacent over the hypotenuse. Well, the adjacent side is a over the hypotenuse is 1. But we know what a is. It's the square root of 1 minus x squared over 1. So that tells us that cosine of theta is equal to the square root of 1 minus x squared, well, over 1. So cosine of theta is the square root of 1 minus x squared. And that's exactly what this quantity is right here. So we just plug that in right over here. So that tells us that the derivative with respect to x of sine inverse of x is 1 over cosine theta, but that's the square root of 1 minus x squared. So if we just put that over here at the title of this slide, the derivative with respect to x of the inverse of sine is 1 over the square root of 1 minus x squared. And this is our desired formula. Let's do the same thing for inverse cosine. And in fact, it really is the same thing. The computation is almost identical. So let's do it the same way. We start with cosine of cosine inverse of x. And by the cancellation law, this is equal to just x. And so what do? We compute the derivative of both sides with respect to x. The term on the right is the derivative of x with respect to x, so that's just going to be 1. But on the left, we have the derivative of a composition, so we have to use the chain rule. So we have the derivative of cosine of a thing. The derivative of cosine is the opposite of sine of whatever that thing is going to be, times the derivative with respect to x of whatever that thing is. And, like before, we know what that thing is. It's cosine inverse. That's the inside function, so we just plug it inside. So we just put cosine inverse of x, and we put it inside here too, cosine inverse of x. So if you differentiate cosine of a thing, the derivative of cosine is the opposite of sine of that same thing, but then we have to multiply by the derivative of that thing. Now we don't know what that is. In fact, our goal is to find this. So we want to solve for this. And we can do that because on the right, we have the derivative of x with respect to x, so that's just 1. The derivative of x with respect to x, that's that 1. Okay, so we solve for the unknown quantity, namely we divide by the opposite of sine of cosine inverse of x, and we'll have that the derivative with respect to x of cosine inverse of x is equal to the opposite of 1 over sine of cosine inverse of x, like so. And once again, we have the same problem that we had before. We have sine of inverse cosine, and we can express this in terms of radicals and x's. And let's do that exactly the same way that we did before by means of a triangle. So we'll just draw a dividing line here. So we want to compute sine of cosine inverse of x. We want to determine what that is. And once again, we're going to let cosine inverse of x be some angle theta. So what we're really trying to figure out is what is sine of theta. That's our objective. Now what we know is that cosine inverse of x is equal to theta. So that means that x is equal to cosine of theta, because cosine inverse is the inverse of cosine. And we know that cosine relates to a triangle. And in fact, remember that cosine of theta is adjacent over hypotenuse. So if we construct a triangle, let's construct a right triangle just like we did before. And let's make this angle theta. Cosine of theta is the adjacent over the hypotenuse. But we know that it's equal to x. So if we make it so that this length is x, then the hypotenuse will have to be equal to 1, because the adjacent over hypotenuse is x over 1. And we know that cosine of theta is equal to x. Now what we're doing is we're constructing a right triangle so that this angle is theta, and we just make sure that this length is x. And if that's the case, if this length is x, then the hypotenuse has to be 1. Now what we're looking for is sine of theta. And what is sine of theta? Sine of theta is opposite over hypotenuse. So that means we need to figure out what this opposite side is. So let's just call it b. And by the Pythagorean theorem, we know that x squared plus b squared is equal to 1 squared. So b squared is equal to 1 minus x squared. So b is equal to the square root of 1 minus x squared. So that tells us what the value is for b. Well, sine of theta is opposite over hypotenuse. So sine of theta is opposite, which in this case is b, over hypotenuse, which is 1, which is the square root of 1 minus x squared, divided by 1. So what do we have? We have that sine of theta is the square root of 1 minus x squared. And that's what we're trying to compute. So we just plug that in right over here. So we get that the derivative with respect to x of cosine inverse of x is equal to the opposite of 1 over, and now we just plug in the square root of 1 minus x squared. And let's just put it up here. So the derivative of the inverse of cosine is the opposite of 1 over the square root of 1 minus x squared. And this is our result. We're going to do this for one more inverse trigonometric function, namely the inverse of tangent. This is similar, but the answer ends up being slightly different. But we begin in the same way. So we'll start with tangent, evaluated at tangent inverse of x is equal to, using the cancellation law, just x, like so. And now we're going to do what we did before, which is differentiate both sides. So we'll differentiate both sides with respect to x. And just like before, on the right side, you're going to just end up with a 1. Let's just move that down a little bit. On the left side, you have a composition. It's the derivative of tangent of a thing. Well, the derivative of tangent is secant squared. So it's going to be secant of something, quantity squared, times the derivative of whatever's inside there. And what is inside there? Well, it's tangent inverse. So as usual, we just have the inverse function, and so we just stick that inside. The derivative of tangent of a thing, the derivative of tangent is secant quantity squared. So the whole thing, secant whatever, is squared. So the derivative of tangent is a secant squared. Now it's secant of a thing, and then we have to multiply by the derivative of whatever that thing is. Now in this case, that thing is inverse tangent. So let's just write in tangent negative 1x, and here too, tangent negative 1x. And what is this all equal to? It's equal to the derivative of x with respect to x, which of course is just 1, just like before. So if we just underline that, just to indicate that it's the same. Okay, so this quantity is what we want to solve for. So solve for this. And we're going to do it in the same way that we did before. So the derivative with respect to x of tangent inverse of x, we just divide by everything else. Divide by this secant squared term, and you'll end up with 1 over secant of some quantity, and all of that is squared. Now that quantity happens to be tangent inverse of x. But now we have the usual problem, which is that we have a trigonometric function evaluated at an inverse trigonometric function, and we can write this as something algebraic. And we'll do what we did before, which is construct a right triangle. Now in this case, the thing we're trying to solve for is secant of some value. So it's tangent inverse of x. And we want to determine what this is. So we're going to call tangent inverse of x theta. So that's going to be some angle. So what we're trying to figure out is what secant of that angle is. And if we can figure out what secant of that angle is, secant of that theta, that's just this. So if we can figure out what secant of theta is, then we can just plug that in here. And of course we'll have to square it, but we can do that. Okay, so how are we going to do this? Well, we're going to draw a triangle again. So the triangle, it's going to be a right triangle, just like before. And we'll call that angle theta. But this is a secant, and maybe we have to remind ourselves of what secant is in relation to the right triangle. So secant of theta is 1 over cosine of theta. And cosine of theta, remember, is adjacent over hypotenuse. Our goal is to figure out what secant is, and that's 1 over cosine. And we can figure out what cosine is if we know what the adjacent and the hypotenuse lengths are. Well, how are we going to figure that out? What do we actually know? Well, what we know involves this tangent. We know that tanverse, so tangent inverse of x is equal to theta. So that means that x is tangent of theta. And tangent is opposite over adjacent. So in our triangle here, if we construct a triangle so that this angle is theta, and we pick the opposite side to be x, like so, then we'll have x over the adjacent. But that has to be equal to 1. Why does that have to be equal to 1? We're constructing a triangle, and we ensure that this angle is theta. And if we know that that angle is theta, then tangent of theta will be opposite over adjacent. So if we make sure that this triangle has opposite side equal to x, then opposite over adjacent has to be equal to x. But we already know that the opposite side is equal to x, so the adjacent has to be equal to 1. So that's this. Now the thing that we're trying to figure out is secant of theta, and we're doing that by figuring out what cosine of theta is. That's adjacent over hypotenuse. We know what the adjacent is, it's right here, it's 1. But we need to figure out what the hypotenuse is. So let's just call that c, and then using the Pythagorean theorem, we know that 1 squared plus x squared is equal to c squared. Or in particular, c, the thing we're looking for, is the square root of 1 plus x squared. So that tells us that cosine of theta, which is adjacent over hypotenuse, is equal to 1 over c. But what is c? It's the square root of 1 plus x squared. So it's 1 over the square root of 1 plus x squared. But we're actually interested in secant theta. So secant theta is 1 over cosine theta. Well, we know what cosine of theta is, so secant theta is just the reciprocal. So secant theta is the reciprocal of 1 over the square root of 1 plus x squared. So secant of theta is the square root of 1 plus x squared. So this is the quantity that we're looking for, secant of theta. So secant of theta is secant of the inverse tangent of x, which is right here. So we just take this and plug in the square root of 1 plus x squared. So what is that going to give us? The derivative with respect to x of tangent inverse of x is equal to 1 over secant of theta squared. But of course, secant of theta is the square root of 1 plus x squared. So we have the square root of something squared. So this is just going to be 1 over 1 plus x squared. And that's the derivative of the inverse tangent. So let's just plug that up here. The derivative with respect to x of the inverse tangent of x is 1 over 1 plus x squared. And this is our desired result. Let's use these derivatives that we've just computed to solve some problems. Our first one is find an equation of the tangent line to y equals arctangent of x at the point 1 comma pi over 4. Now let's just remind ourselves that arctangent of x, that's just another way of writing tangent inverse. Now we need a point and a slope. The point is given to us right here. We should probably just quickly check and make sure that this point actually is on the graph, y equals arctangent of x. So arctangent of 1, that's going to give us the angle, so that tangent of that angle is 1, and that's pi over 4. So this point actually is on the curve. Well, we have the point, we need the slope. What is the slope going to be? Well, it's going to be the derivative with respect to x at the point where x is equal to 1. So in order to compute that, we need the derivative with respect to x of arctangent, or tangent inverse. And we're going to evaluate this at x equals 1. Well, we know what this is now. The derivative of the inverse tangent is 1 over 1 plus x squared. So we just want to evaluate this at x equals 1. So our slope, dy dx, at the point where x is equal to 1 is equal to 1 over 1 plus 1 squared, which of course is 1/2. So this is our slope. And we have our point, so our equation is going to be y minus the y value is equal to the slope times x minus the x value. And this is our equation in point-slope form. All right, let's compute another derivative. So we have that y is arcsine, and let's just remind ourselves arcsine, that's another way of saying sine inverse. So in this example, we're asked to compute the derivative of y, where y is equal to sine inverse of e to the negative 3x. So this is a composition of functions. It's a function of a function. So we want to compute dy dx. So this is the derivative with respect to x of, so we'll just put in, well, instead of putting arcsine, we'll put sine inverse e to the negative 3x. And this is the derivative of a composition, the derivative of inverse sine of a thing. So what is this going to be? this is going to be equal to 1 over the square root of 1 minus that thing squared times the derivative with respect to x of whatever that thing is. Okay. Now our input function is e to the negative 3x. This is the thing which is inside. This is our inside function. Our outside function is inverse sine. The derivative of inverse sine is 1 over the square root of 1 minus whatever quantity squared. So whatever that input is, it goes right there. But then we have to multiply by the derivative of whatever's inside. But the thing inside is just this e to the minus 3x. So we just put e to the minus 3x there. And we put e to the minus 3x here. Well, we know what the derivative of e to the negative 3x is. This is negative 3e to the negative 3x. So let's just remind ourselves that the derivative with respect to x of e to the k times x is k times e to the kx. So we're just using that rule here. Now, this actually gives us our answer. One thing that we could do if we wanted, we can simplify this, because here we have e to the negative 3x raised to the 2. So if you have an exponential raised to an exponent, you can multiply the exponents together. So this will give us e to the negative 6x. So now if we put all of these pieces together, we have that dy dx is equal to 1 over the square root of 1 minus e to the negative 6x times negative 3e to the negative 3x. And that's our answer. Let's do something a little bit different. Show that the inverse sine of x plus the inverse cosine of x is equal to pi over 2. Now notice, it doesn't have anything to do with a specific value of x. X is completely arbitrary here. So this is an identity. This is an inverse trigonometric identity. For any value of x, the inverse sine of x plus the inverse cosine of x is equal to pi over 2. Well, let's check and see if this is true. And here's how we're going to do it. We're going to start by defining a function. We'll let f at x be equal to sine inverse of x plus cosine inverse of x. And we're going to differentiate this function. So that's the derivative with respect to x of sine inverse of x plus cosine inverse of x. So we can differentiate this term by term. So we'll have the derivative with respect to x of inverse sine of x plus the derivative with respect to x of inverse cosine of x. And we know what these are. The derivative with respect to x of inverse sine is 1 over the square root of 1 minus x squared. And the derivative of inverse cosine is almost the same. It's just got a minus sign in front of it. So in other words, f prime of x is equal to 1 over the square root of 1 minus x squared minus the same thing, 1 over the square root of 1 minus x squared, which is equal to 0. So f prime of x is equal to 0 regardless of x, or for all x, is how we normally say this. Well, if a function has a derivative that's equal to 0 for all x, that means that the function must be constant. So f is a constant function. That is to say, f at x is equal to c for some c. Well, how do we figure out what that value of c is? So how do we identify c? Well, we know that this function, f at x, is equal to c for all values of x. So all we have to do is just plug in some value of x. So compute f at 0. So this is inverse sine at 0 plus inverse cosine at 0. So sine inverse of 0 is 0, because sine of 0 is 0. What about cosine inverse of 0? Well, that's pi over 2, because cosine of pi over 2 is equal to 0. So that tells us that f at 0 is equal to pi over 2. But we know that f at x is equal to c for all values of x. So that means that f at x is equal to pi over 2 for all x. But let's just remind ourselves what f at x was. Remember how we defined f at x. F at x was defined to be inverse sine plus inverse cosine. So f at x is pi over 2. That means sine inverse of x plus cosine inverse of x is equal to pi over 2. And that is precisely what we wanted to show. Now, in fact, we can do exactly the same thing for a general function that has an inverse. In fact, we can say that if f is differentiable at x, then f inverse is differentiable at f at x. And we can show this using the cancellation laws and the chain rule. So instead of doing it the way that we've been doing it, instead of doing f evaluated at f inverse, what I'm going to do is I'm going to instead look at f inverse evaluated at f at x. So f inverse is the inverse of f, so that's just going to give us x back. And now I'm going to do the same thing that I've been doing, which is differentiate both sides with respect to x. The derivative with respect to x on the left is equal to the derivative with respect to x on the right. And of course, just like usual, the derivative on the right is going to be 1. But what about this thing on the left? Well, on the left, we're looking at a composition. So that's going to be the derivative of f inverse prime evaluated at a thing times the derivative with respect to x of some thing. And now what is that thing? It's the inside function. Well, the inside function is just f. So that goes here and here. So f at x, f at x. And what is this equal to? Well, the derivative of x with respect to x is just 1. So just like usual, this term is that term. But here we have the derivative with respect to x of f. So that's just f prime. So what do we have? We have that f inverse prime of f at x is equal to 1 over f prime at x. Here we just took this f prime of x and we just divided it over to the other side. And this actually gives us our formula. This tells us that f inverse prime at f at x is equal to 1 over f prime of x. And that's really what we said. So we said that if f is differentiable at x, then f inverse is differentiable at f at x. And here it is. Here's the derivative. Here's the derivative of f inverse at f at x. Now, generally speaking, we don't write our formulas in this way. So what we might want to do is we might want to say, okay, this term right here is going to be y. So we know that y is equal to f at x. And in fact, that tells us that f inverse of y is equal to x. So then we're going to take this value for x and we're going to plug it in down here. And that will give us our formula. So we'll have that f inverse prime evaluated at y is equal to 1 over f prime at x. But x is equal to f inverse y. And this gives us our formula for the derivative of an inverse function.